when we look at the different possible solution types to a system of equations, it's easiest first to consider them graphically. For example, we can have two distinct lines that intersect at exactly one point, which gives us one solution to our system. It's also possible that we could have a set of parallel lines, which are not going to intersect at any points, which would give us no solution to our system of equations. The final option is we could have the exact same line with each of our equations, which means that these two lines hit at every single point, which gives us an infinite number of solutions. Now, we know what it looks like algebraically to have one solution. For example, something like the ordered pair 2, 4. But we don't necessarily know what it looks like algebraically if I get no solution, or if I get an infinite number of solutions. So we're going to go through two examples that are going to show us algebraically what it looks like to have those types of solutions. In the first example, we're going to consider this system of equations. We're going to solve it using elimination. And if you notice, everything's already lined up. The x's, the y's, the equals, the numbers. So I can go right to finding the additive inverses. So I look at the coefficients, -3 and -6, 5 and 10. And unfortunately, they all have the same sign. So I'm not going to get inverses with the same sign. So I'm going to have to multiply one of them at least by a -1. And I also notice that if I multiply the top by a -2, I can get additive inverses on the x term. So I'm going to go ahead and multiply the entire top by -2. Remember to distribute that through to every one of my pieces. So this gives me the new system, 6x minus 10y equals -14. The bottom equation stays the same, -6x plus 10y equals 3. I get what I want with the additive inverses on the x's, 6 and -6, so those cancel out. And I also get -10 and +10 for the y's, and those cancel out, which leaves me with nothing on that side of the equation, or 0. On the right-hand side, when I add -14 and 3 together, I get -11. Notice how all the variables cancel out. No x's, no y's left in the problem. And I'm left with a number statement. 0 equals -11. And I'm pretty sure that 0 does not equal -11. It's a false number statement. And anytime I get a false number statement, it's telling me that my system has no solution. And if I have a system with no solution, I have a set of parallel lines that never touch. If you want to confirm that, put each of those into slope-intercept, and you'll see that they're parallel. So my final answer to this system is that there is no solution. For my second example, I want to look at a system and solve using substitution. When I go to solve using substitution, again, I consider all of the coefficients and look for a plus or minus 1, something easy to solve for. In this case, I don't get that. But if I look carefully, I notice that the -2 here is going to work out well. If I divide through by everybody who's divisible by 2, I'm going to end up getting nice integer coefficients on my answer. So my first step here is going to be solve equation 2 for x. So I take -2x plus 4y equals 6 and begin to use inverse operations to take the 4y over. So I get 6 minus 4y. Divide everybody by -2, so x equals -3 plus 2y. Remember, with substitution, my goal is to solve one equation and plug it back into the opposite equation, not the same one. So I'm going to take this up to the first equation and plug him in for x. That gives me -3. What was once x is now -3 plus 2y plus 6y equals 9. This is one equation with one variable, which is way easier to solve. So I distribute the -3 and get 9 minus 6y plus 6y equals 9. Combine like terms, the y's cancel out, and I end up with 9 equals 9, which is a true statement, and that's a great statement, but I already knew that 9 equaled 9 before I started the problem. So you have to say what that means. And what that means in this case, since it is a true number statement, is that I have an infinite number of solutions. Which means that I have the same line. It's dressed up a little bit differently with different coefficients, but my final answer is infinite solutions. So true number statement, infinite solutions, false number statement, no solution.